Hi guys, this is Dr. K. I wanted to sort of pre-lecture the third part of the alkenes chapter because the exam is coming up on it very quickly. And this will give you a chance to see some of the material before I lecture on it, to give you a better chance to learn the material and know what kind of material I expect you to know for the exam. There are really a couple of key things that I really want to cover before the exam. And principally, they involve two areas. One is E2 reactions. And in E2 elimination, what I want to cover in this pre-lecture is to cover the effect of base size, two, bad leaving groups, three, stereochemistry of the E2 reaction. And then really the last big topic to cover about E2 reactions and E1 reactions is to talk about competition between types of reactions. Now the last two sections in this chapter, we're going to save those for the next exam. And in that section of the chapter, what we do is we look at the substitution and elimination reactions and how they either cooperate or compete with each other depending on the solution conditions. So what we're going to do, though, rather than cover that in this exam, is I want you to do something that is the lead up to that, and that is evaluating nucleophiles and bases. By the way, this picture that you're seeing is from the science show last year, and it's one of my favorite shots of Mr. Balo igniting a giant hydrogen balloon. We didn't do it this year, but I have a feeling it's going to come back to us when we do Pi Day in March 14th. Okay, so if you keep that in mind, maybe you can join us on the Friday near Pi Day, and we'll not only have a pie in the face contest, but we'll also have another science magic show. All right, so let's sort of start on with the lecture, so I'll get that distracting background out of the way. So what we want to look at is the effect of the size of base and also bad leaving groups on the regioselectivity of a reaction. Now, if you remember, E2 reactions are regioselective. So very quickly, we're going to do E2 mechanism. I'm just going to give you a base. This is the alpha carbon. These are betas. And what you have to look at is beta elimination. You got to look at the elimination of the hydrogens on that atom or on that molecule. And the hydrogen atoms get selected by the base and lead to the products. And what we find is that in general there are two possible products. For the elimination of beta 1, you'll get this. For the elimination of beta 2, you'll get this. And in most cases, when you have small bases, let's say methoxide ion, for example, E2 dominates because of stability. And so we looked at stability of alkenes, and alkene stability has to do with several different factors. The ones that are most obvious are number of substituents, 1, 2, 3, and 4 substituents. This one in particular has 2. So, but 2 substituents, this one has 1. And as a result, this is the more stable product that's circled here. And we say it's more stable because of the inductive effect of the methyl groups, or the alkyl groups that we find on this end of the pi bond and this end of the pi bond. So we have 2 alkyl substituents. They donate electron density, you could either say by hyperconjugation or by induction. And that causes the more electronegative pi bonds to pi bonded carbon atoms to become more stable. If you remember, our discussion about that is that the pi bonds indirectly, those pi bonds, not indirectly, but those pi bonds are on sp2 carbons, and that causes the orbitals on those atoms to be slightly shorter, and the electron density is held more close to the nucleus, and so as it turns out, those bonds tend to be stable, those carbons tend to be stabilized by alkyl substituents. Okay, so we'd covered all that. Now, the other thing, though, that we need to cover is what happens if you have a bad leaving group, or what happens if you have a bulky base. And it turns out that when you have a bad leaving groups or bulky base, so let me put that down. Okay, so bad leaving group or bulky base leads to, in an E2 reaction, the anti-Zaitsev product, or the less stable double bond. Now, how is it that you could form a less stable double bond, now think energetics, and have it form faster? Okay, so the answer, without getting into all the details, is that must be the one that forms faster. It's the kinetic product versus the thermodynamic product. I know I've been harping on that, but that's an important concept to get across. So let's talk about bulky base. So let's say this is our alkyl halide, and this is the hydrogen that's going to be eliminated, or this is the hydrogen that's going to be eliminated. So if the base is large, so for example T-butoxide, so these are hydrogens, and just sort of illustrating the point by drawing it all out. This is a very sterically hindered base. That is, it has a hard time getting to this hydrogen. So this hydrogen is got groups around it that keep the base from approaching it as easily, because it is the more substituted carbon. And this hydrogen is easier to get to because it's the less substituted hydrogen. So as it turns out, this reaction is faster. The reaction to this beta hydrogen is faster. And as a result, we have the favoring of a kinetic product rather than a thermodynamic product. So this produces this as the major product. This upper one leads to this as a major product. Now, This one's more stable. This one is less stable, but it forms faster. So large bulky bases can favor the less stable product. Now, we should also talk about the effect of leaving groups. So I'll give you a little bit of data. We're going to take an alkyl halide that looks like this. So this is the halide. Let me redo that. This is my halide. And we're going to look to see what happens when X is equal to iodide, bromide, chloride, or fluoride. Okay, so when X comes off, it'll be X minus. And we're going to have elimination with methoxide ion. So methoxide, remember, alkoxide ion, CH3O. It's methanol with a minus charge. Probably a sodium methoxide in methanol. We form two products. So the product on the right, this is the anti-Zaitsev. The product on the left is the Zaitsev. And we're going to look at the percentages that we get of each. Okay, so Zaitsev product is about 81 versus 19 for iodide. Now, iodide is a good leaving group. For bromide, it's going to be around 72 to 28. And when we get to chloride, it's down to 67 and 33. And then when you get to fluoride, the percentages flop. 30% versus 70%. So we end up with the preponderance, or the more of the anti-Zaitsev product when we have a bad leaving group. A clue into why this happens has to do with the pKa values. The pKa value for iodide, or HI, the conjugate acid, is minus 10. So if you look at HBr, that's minus 9, and HCl, that's minus 7. And what does this tell you about these leaving groups? These are all good leaving groups. However, fluoride, the pKa is around 3.2 if you look it up. Okay? So what does that make fluoride? It's a much worse leaving group than HI, HBr, HCl. Of course, it's better than things like hydroxide, but typically when we eliminate hydroxide, we protonate it, and then it becomes a good leaving group. The pKa of the protonated alcohols is typically around -1 or -2. All right, now, why might this be? So what we need to do to understand why, again, we get a kinetically favored, less stable product, we have to think about transition state. So take a simple example. I'm just going to use the alkyl halide. That I seem to always gravitate to as a 2-bromobutane. And then we're going to think about the transition state. Again, I have two beta hydrogens. I have one here and one here. When a base comes in and attacks at this point, this bond collapses and the bromine leaves. Again, that's the mechanism. It's a concerted mechanism for the elimination of HBr. If bromine is a good base, then what happens is, is a good leaving group. When the base grabs the hydrogen, it's very easy for this bond to collapse because the bromine is just going to leave without much resistance because of its conjugate acid's very high pKa, or very low pKa. On the other hand, when you look at a bad leaving group, the bad leaving group looks like this. And we'll do fluorine. And I'm going to give myself a little bit more room. I'll just set it out in the middle over here. Here's my fluorine. And here's a hydrogen. Strong base comes in and grabs this hydrogen. Now, here's the deal. This fluorine doesn't want to leave. The reason it doesn't want to leave is this bond is relatively strong. So essentially what happens in the transition state for this molecule, the base has to essentially bond almost completely to the hydrogen, and this hydrogen ends up pushing negative charge onto the carbon it's attached to. So in the transition state then, what we think about is for this kind of molecule that the transition state has the fluorine here, a dashed bond to the hydrogen, and the base attacking it. Now, what kind of base is this? Well, it has to be a reasonably strong base because otherwise the fluorine won't get kicked off. So reasonably strong bases have negative charges on them. Okay, so now, because this is a transition state, over here it would be negative, not partially negative, but here it'll be partially negative, and then here this is partially negative. That is, as the base pulls the hydrogen off and pushes the negative charge onto the substrate, that negative charge is going to build up on this carbon, or if the transition state is to this carbon, then on that carbon. Now, we talked about carbocation stability, and for carbocations, what we have is the following trend. And I'll leave methyl out of it because we don't really use it for that much, except for methylation reactions, of course. But I'll just talk about primary, secondary, and tertiary. And the most stable is the tertiary. And the reason that the tertiary is the most stable is essentially the same reason that pi bonds are more stable when they're more highly substituted, and that's because the alkyl groups will push charge onto the carbocation and stabilize it. So if carbocations are more stabilized by alkyl substituents, it turns out the exact opposite is true for carbanions. So for carbanion stability, we'll have primary, secondary, and tertiary. Primary carbanions are the most stable. So when you think about activation energy, remember this mechanism is E2. I'm going to call this beta 1 and beta 2. Energy diagram might look something like this. So, let's say this is the elimination at beta 2. that product is going to be more stable because beta 2 is going to give me the internal alkene, that is the 2-butene product, whereas beta 1 is going to give me the less substituted terminal alkene. But the deal is that it goes through a carbanion-like transition state. So just based on our analysis of what we've looked at already, it has to have a lower activation energy. I wasn't very careful about where I put beta 1, unfortunately. I think beta 1, generally when we draw these, is going to be lower than this, but it doesn't necessarily have to be. It still is a faster forming product because it has lower activation energy. Its low activation energy is attributed to the stability of the anion, or the negative charge, on the primary carbon versus the negative charge on the secondary carbon. So, just sort of reviewing, bad leaving group. These have pKa's that are much higher than, for example, bromide and chloride in the 3 to 4 to 5 to 6 range. And then when the the base comes in to pull the hydrogen off, the worse this leaving group is, the higher the charge is that has to build up on these two carbons. As a result, when you have elimination at the primary carbon, the activation energy is lower, but you end up getting a less stable product as a result. Okay, same energy diagram, by the way, can be used for elimination of bulky bases in E2 reactions as well. Okay, so what we'll do next is we'll talk about sorry, I got a little distracted, so there might be a little bit of a break here in this lecture, but got caught up in the Fresno State football game. Anyways, we'll talk about the stereo specificity of E2 reactions. And when we say stereo specific, what we mean is that when you have a reaction, it produces a single stereoisomer as opposed to two stereoisomers. So there's actually two terms that you need to know out of this section. There's stereo specific and stereo selective. They have similar meanings, but stereo-specific means that when the reaction takes place, only certain isomers are produced, or only one isomer is produced, let's say out of two. And stereo-selective means that there could be multiple products of a specific stereochemistry. Another distinction of stereo-specific is to think of something like this as well. It could also mean a subset of reactants with certain stereochemistry, form products, and also can mean that a reaction produces, in terms of products, one stereoisomer, for example. Stereoselective, on the other hand, can be reactions not necessarily thinking about what the reactants look like, but produce one type of stereoisomer regardless of the stereochemistry of the reactants. So if you get one product favored, that's typically a stereoselective reaction. So that could be cis or trans versus cis, for example. And this is based on factors like steric strain that cause the formation of the trans product to be more predominant. So what we're going to talk about, though, for E2 reactions is stereospecific reactions. And so what I have is, for example, a molecule that looks like this. And then I have hydrogen here, and then I have a base. And let's say it's not sterically hindered, so it's going to be an E2 mechanism. The base will attack the hydrogen, collapsing that bond and causing that group to leave, the bromine to leave. The result is a double bond between these two carbons, here and here. And I'm going to call this R1, and I'm going to call this R2. So those could be any groups as long as they're not the same, okay? Now, so you get a product, and it turns out the product might look like this. Or it might look like this. So which product you get actually is determined by the mechanism of the reaction. So one of the key features of E2 reactions is that the hydrogen, the beta hydrogen that is eliminated, needs to be anti to the leaving group. Now, just to review really quickly, anti means if you do the Newman projection, the beta hydrogen has to be anti to the leaving group. The reason for this is that there's a couple of ways that people try to explain this. I'll give you sort of the simple answer, and then I'll give you probably the more complete and probably more accurate answer as well. The simple answer is that the E2 reaction is SN2-like. In the sense that the electrons, the beta hydrogen electrons, do a backside attack on the leaving group. So when you think about just the Br, for example, and the H that are eliminated, when a base comes in, it attacks this hydrogen. That group, those electrons, do the backside attack on the bromine, and then the bromine leaves. Now, probably a more accurate description of what's going on, although it's very related and similar, is that when you think about the hydrogen being bonded to the bromine, the hydrogen being bonded to the carbon and the carbon being to the bromine, these bonds are made out of orbitals. And, that's a bad sp3 orbital. So these orbitals. Turns out this alignment of these two orbitals is much better in this position than in this position. So the electron density is going to flow from this bond here into this bond here as the bromine leaves with the electrons that are in this orbital. So that being the case, that either one of those explanations is often used for describing what goes on in an E2 elimination reaction. So let's go back to the reaction that we were talking about. Let's examine a couple of different scenarios. So what I'm going to do is copy this molecule that we have here onto the next slide, and we'll see how those things look in Newman projections. Make sure I copied that correctly, yeah. Okay, so now, when you're doing this, sketch in the hydrogens that are there to help you draw your Newman projection. And then imagine that we're looking down this axis. You could look down the other way as well, but that's our perspective. So this is the front carbon, this is the back carbon, and so you draw your Newman projection. So I'm going to draw the CH3 group in the front up, and since I'm looking at it from the front, with the H is going to be on this side, and the Br is going to be over here. I have the other groups over here. So I have a hydrogen in the back. I have R2 up here, and at the bottom I have R1. Now if you notice, this is the beta hydrogen that's going to be eliminated, and this is the leaving group, and right now they're not in the anti-configuration. So what I'm going to do is rotate the Newman projection so that the beta hydrogen and the leaving group are anti to each other, and just because I prefer doing it this way, I'm going to leave the front of the Newman projection alone, and then I'm going to rotate the hydrogen, that is this hydrogen here, to this position, and this R2 is going to go, oops, didn't mean to hit that, R2 is going to replace R1, and R1 will be where the hydrogen is. Okay, and that will get that hydrogen anti to the leaving group. Okay, so I have a hydrogen here. Oops, meant to do that in white. Hydrogen there. R2 here. And R1 over here. So when these two groups are eliminated, what's going to end up happening is that these groups will end up being on the same side. Sorry, that's a CH3. And these two groups will end up being on the same side. So in terms of my stereoisomers, that's going to leave me with, starting with this, the double bond ends up in between. The hydrogen in R2 will be on the same side, so I'll put hydrogen down here. Oops, didn't mean to put that mark there. In R2, this is the CH3. And this is R1. So this is the only stereoisomer, or I should say, it is almost entirely the almost stereoisomer that is obtained from this reaction. There's probably a small amount of the other one, but not very much. Okay? So let's do another example. So for our example, what we're going to do is we're going to steal a problem from the book, and it's 818 is the problem. And the molecule is going to look like this. So there's the molecule. Now, I'm just going to call this T-butyl. This is Me, and this is going to be phenyl. And then we're going to draw the Newman projection, and to make this Newman projection, I'm going to look at it from this perspective here, and then we'll decide what the conformation of the cis and trans, the double bond is going to be after we figure out which way the elimination takes place. So in the Newman projection, I'll draw a circle, and then I have a group coming straight down. The group coming straight down is this one here. This bond here, it's in the plane and is going straight down. That means I have two other bonds that go like this. And this is going to be my T-butyl. In the back I have bromine, and in the front I have a hydrogen. And then the others will look like this. And in the front I have a methyl that's on this side. Which means in the back I will have a hydrogen. And then I'll have the phenyl group pointing up over this way here. That's up when you're looking down in this perspective here. So if you look at that, what you see is that the groups that I want to eliminate will be the leaving group and the beta hydrogen. So these are not anti to each other, so what I need to do is I need to rotate this over. I need to take the hydrogen and move it to here, because it needs to be anti to the leaving group. The methyl will take the place of the phenyl group, and the phenyl will hop over here to where the hydrogen is. So having done that, I'll redraw my Newman projection, or at least on paper having done that, I will redraw this. I'm going to leave the front alone, because that's just, I find it's easier in my head to keep track of things if I always do it the same way. And then I'll draw in my other groups. So we have the phenyl group here, and then we have the methyl group up at top, and then I have my hydrogen here. So now when I do that, what ends up happening is these two groups will be together, and these two groups will be together as the pi bond forms. So that is a base will come in, take that hydrogen, that collapses in, and that leaves. The pi bond the pi bond is being formed by that pair of electrons. So we're going to draw a double bond. And like that. I will stick all the groups on it. And I said T-butyl and phenyl will be on the same side, so I'll put those down here. And then the hydrogen and the methyl will be together. Now the hydrogen is sitting with the T-butyl group, so the hydrogen's on this side. That is, what I'm doing is I'm looking at T-butyls here, and then the hydrogen is up here. Those are both on the same carbon. Okay, so I have the phenyl and the T-butyl group on the same side, and the hydrogen and the methyl group together. So, if you notice what happened, ended up putting the two largest groups together. That's not what you would have predicted from a stereo selective reaction. You would have expected the larger groups to be opposite of each other. So this is the particular stereoisomer that you get from the reaction here. Now, a special instance of this type of reaction occurs on rings, and so let's very quickly review what a cyclohexane ring looks like. Ooh, that's a horrible ring. Here, let me do this. Oops. Okay. A little over tilted from where I drew it, but that's okay. On a cyclohexane in the chair configuration, we have axial hydrogens here, 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 and it's 6 axials like this, and 6 equatorials, for example, like that, that, and that. Okay, so now let's think about this. E2 anti. The groups on this ring that can only be anti are these guys. The axial positions are the anti positions on the ring. So if you look at the Newman projection, for example, looking down in that direction, and I'm going to call this R1 and R2, R3, and R4, just kind of randomly numbering these things. Newman projection like this. Now I have R2 going down, that's my axial. I have R1 going up like that. R3 is up here, and R4 is down here. And this connects to the rest of the ring. Okay. These groups are axial. Now, if you flip the ring, and this is just kind of a review, if you flip this ring, that means the other end goes up, that is, this end will be pointing up, and this end will be pointing down. So I'm going to draw it like this. Oh gosh. That. Then the axial and equatorial flip. And in particular, just on the 2 carbons I'm really paying attention to, this is R4 and R1, and this is R3 and R2. And you'll notice that R3 and R4 are now axial to each other and could be eliminated if one was the leaving group and one was the beta hydrogen. Okay, so something to keep in mind that at all times is that these two structures are generally in equilibrium with each other, and the ring is flipping back and forth. So let's look at a specific instance of how this might affect stereochemistry, and we're going to look at two similar molecules, both cyclohexanes. One's going to be like this, and the other will be this. And let's look to see what kind of products we can get out of these two. Okay, so now these ones are an adjacent and they're trans, and these ones are an adjacent and they're cis. So let's draw a chair. Oh gosh, it's so hard to draw this on this. There's a chair, and I'm going to put the methyl down, and the bromine will be up. So what does up mean? Trans would be like this. Now, there's a hydrogen here, and a hydrogen here. So you notice that the way I've drawn this, or the way I ended up drawing it first anyways, is that the bromine can't eliminate to the right. So what we need to do is we need to check to see when the bromine can't eliminate at all. When the bromine is in the axial position, is there a hydrogen that can be eliminated? So I'm going to redraw it. I'm going to flip the chair, which means the methyl will be axial, and the hydrogen is going to be equatorial. The bromine will be the axial group here, and the hydrogen will be equatorial. If you notice, this is a methyl group, there's the leaving group. Elimination can't happen between this particular leaving group here and a beta hydrogen on the methyl group, or the carbon containing the methyl group. However, just to be clear, there are hydrogens on this side. Ooh, that was bad. Hang on. And this hydrogen is actually anti to that bromine. So in the end, the product that you would get out of this elimination reaction is this. Now let's look to see what happens to the other ring. And I will draw a chair. And I will put the bromine here in the up position, and the methyl group here in the up position. And again, you have to consider the hydrogen that's on that beta carbon and the hydrogen on two hydrogens on this beta carbon. Gosh. Now, as it is, the way it's drawn, that bromine can't be eliminated because it is in the equatorial position, so I need to flip the chair. Now, it might turn out, though, when you draw it the first time, that the chair, you draw the bromine in the axial position. But if it doesn't, then you just redraw it in the flipped chair configuration and put the bromine in the axial position. And on the beta carbon with the methyl group attached, this hydrogen is now axial. So there can be an elimination on this side, and there can be elimination on this side. So here's my alpha, these are my two betas. Okay? Now, when you think about the possibility of doing elimination on both sides, what you find is that you'll end up with either this product or the product that I had drawn before. Now, notice that this double bond has 3 substituents on it, and this double bond only has 2, so in fact that's the less stable isomer, or constitutional isomer, so this is the product that actually forms because it's more stable. One last thing that I wanted to point out is, what if you have a chair? I got to draw these lines one at a time. What if you have a chair that looks like this, or one that looks like this? Sorry, let's make that a methyl group. Okay, so question would be, which one reacts faster? And it'll turn out that the answer is this one, but you have to understand a little bit about the dynamics of what's going on with this molecule. Remember, chairs will flip back and forth, so you could end up with this some of the time. Ooh, that's horrible. Sorry. Or you could have this molecule that I originally drew some of the time. Well, which one do you have more of? Well, it turns out, just based on stability and what you understand about stability, that this particular conformer is more stable. So when we think about rates of reactions, one of the things we think about is molecules have to collide with sufficient energy, but they also have to have the correct orientation for the reaction to take place. In this particular molecule, the correct orientation is also the more stable conformer, and we know from earlier conformational analysis, the more stable conformer is the form that the molecule will be in most of the time. And as a result, it's going to be in the right position for elimination more often than it is not. On the other hand, this particular molecule is going to be in an equilibrium with this. So it turns out this is more stable, but the bromine is not axial. So the bromine can't be eliminated in this case. As a result, because this is the more stable conformer, the molecule is in the incorrect orientation for elimination to take place more times than it is not, and as a result the rate of reaction will be lower because the molecule is not in the correct configuration most of the time. So one last thing before we finish up, and I know it's a full lecture, so it's going to probably getting a little tired now, so you might want to take a break, but what I want you to start thinking about is the following. And we'll actually spend more time on this after the exam as well. We have talked extensively about nucleophiles. And nucleophiles we sort of categorize as good or bad. Good nucleophiles, typically we say have a pair of electrons, negative charge, pi bonds, things like that, and those make for good nucleophiles. Bad nucleophiles tend to be neutral in charge. But they still have to have the pi bond or the pair of electrons that can be donated. So something like Cl minus. Sorry, I did something. I'll have to back up here just a second. Let's leave the pi bond out of this for now. A bad nucleophile is something that has a pair of electrons but doesn't necessarily have a negative charge. So when we think about good nucleophiles, we might think about OH minus. But a bad nucleophile would be the conjugate acid of that, which would just be H2O. So OH minus, good nucleophile. H2O, bad nucleophile. Same thing could be done with, for example, alkoxide ions. CH3O minus, that's a good nucleophile. And again, it's going to be in the form of something like sodium methoxide. Or we could look at methanol, CH3OH. That would be a bad nucleophile. So those are some of the characteristics that we talked about for good nucleophiles. We also talked about size of the atom, and really this boils down to what we call polarizability. So polarizability really has to do with size and the number of electrons, and larger atoms tend to be more polarizable and tend to be better nucleophiles. So for example, H2S or HS minus, those are both good nucleophiles. Even though H2S is neutral, it's much more polarizable. This would be the sulfur analog of water. Much more polarizable, it's a better nucleophile. Now, in elimination reactions, we talk about bases. And we categorize bases as good, strong, or weak. In strong bases, we talk about things like alkoxide ion, CH3O minus, or hydroxide ion. And so we have a general idea in our heads when we start all this stuff, is that, strong bases are good nucleophiles. But it turns out that that's not always the case, because H2S and HS minus are both relatively weak bases, but still good nucleophiles. So, one of the things that we'll consider after the exam is that if you have a strong base and it's not a good nucleophile, it's going to favor elimination. Again, it actually depends a little bit on substrate. But if you have a strong nucleophile that's not a strong base, for example, like H2S or HS minus, those are better nucleophiles than they are bases, and as a result, that's going to favor, for example, SN2 reactions on primary alkyl halides. There's a couple of other interesting comparisons to be made in this whole polarizability argument. Hydride containing compounds. For example, NaH tends to be a bad nucleophile, but it's also a very strong base. But lithium aluminum hydride tends to be a good nucleophile, and it's also a strong base. The reason being is the aluminum hydride ion is much larger than just hydride itself, and as a result is more polarizable and has a tendency to act more like a nucleophile than sodium hydride, and there's less substitution with sodium hydride and more elimination with sodium hydride, whereas with lithium aluminum hydride, given that you have a good electrophile, lithium aluminum hydride tends to be better at doing addition of hydrogen as a nucleophile rather than simply acting as a strong base. So what we're going to do is I want you to think about the following. We're going to classify nucleophile as either being good or bad, or good or bad, and bases as being strong or weak. And think about 4 different ways that you could categorize nucleophiles / bases. They could be good nucleophiles that are strong bases. So for example, the lithium aluminum hydride, or more commonly alkoxide ions. You could also have good nucleophiles that are weak bases. So for example, SH minus. You could have strong bases that are bad nucleophiles. So for example, H minus, or your book talks about DBN or DBD. These are both bases that are bad nucleophiles. And then you could have weak nucleophile and bad nucleophile and weak base as well. So those would be things like ROH or H2O. So what we're going to be working on in the next section following the exam is taking this classification and then looking at substrate types and determining whether or not a reaction will go by SN1, SN2, E1, or E2. So that kind of ends this lecture, and I'll be covering a few other things in the actual class lecture, including going over the entire mechanisms for SN1, E1, SN2, and E2.